Good morning, candidates. Welcome to the CI session of 2020.
Guys, it's that time of the year. It's gonna be Squid Game season with everything happening. And let's not forget about the war that is also happening at the same time. So hopefully like these examinations actually take place and everything works out well. But anyways, today we're gonna be doing some difficult physics questions, paper 4. So without further ado, let's just get right into the video. Alright, let's start off with a question about moments. So here we have a balanced uniform meter rule made of wood. And we can see the whole arrangement over here. It looks confusing, but don't worry, we're going to go over this one by one. The width of the meter rule is 2.6 times 10 to the power minus 2, and the thickness is this. Always keep in mind not the value but the units, because the units will essentially help you get to the formula easier. On figure 2.1, mark the position of the center of gravity of the meter rule with a point labeled x. Label the distance of x from the 0 centimeter end of rule. Okay, so we can clearly see that this is a scale extending from 0 to 100 cm. So if you think about it logically, if you have a scale that goes from 0 to 100, the center of gravity will usually lie in the midline between them, which is going to be 50 cm. So we can see that we need to draw 50 cm, which would be somewhere right to the pivot because the pivot is at the 42 cm mark, and it is going to be left with the 80 cm mark. Why? Because again, center of gravity is always located in the midline. So in between these two measurements, we can say that this might be like around 60, it's like the midpoint. So we can say that this is where 50 cm is located. Show that the mass of the meter rule is 0.081 kilograms, and this is going to be a 3 marker. Essentially, what we need to do is, we know that this is a uniform balanced. They're telling you that this isn't moving. There's no resultant moment, there's no resultant force. So that essentially means that whatever the total clockwise moment is being applied towards the left side is going to be equal to the total anti-clockwise moments being applied from the left side. So we're going to start off by saying that the total clockwise moments is equal to the total anti-clockwise moments, the ones that are moving from the right to the left side. Like this is a clock. Like if you imagine a clock, it's like moving clockwise. So we can see that there's only two forces over here. We're going to have the weight acting, and we're going to have the force over here. So the total clockwise moment is going to be the weight times the distance from the pivot, plus we're going to add the force that was also being applied times the distance from the pivot. This is going to be equal to the total anti-clockwise moments, which if you look above, is only going to be 1, which is 0.34 newtons. Force 2, for example, times distance. Now that we have this equation set up, we know that weight is unknown, but we know the distance, which was 8 centimeters. Now, if you look back, you can see that the distances are as follows. The pivot is at 42, the weight is at 50, so the difference between them will be 8. The pivot is at 42, this force over here is at 80, so the difference should be around 38. And then over here, the difference from the 0.34 Newton force and the pivot should be 32. But again, these are all centimeters, so we should convert them into meters by dividing them by 100. Now, what did we find out? We found out the weight. So since the weight is 0.79 newtons, we know that the formula for calculating mass is going to be weight divided by the gravitational field strength, because we know that the formula is W is equal to mg. So if we make m the subject, then you get my point. So we're going to get to mass is equal to 0.79 divided by 9.8, which should just give us this value over here. That is 0.081. Moving on, calculate the density of the wood of the meter rule. This isn't that difficult. We know the density is rho is equal to mass times volume. We figured out the mass, which was 0.081 kilograms, but we need the volume. So over here, we know the width, we know the thickness, which is also mentioned, and we also know the length, which is 100. So essentially, since volume is length times width times height, so hopefully you guys didn't skip maths. So we know that we have the length, we have the width, we have the height. We just need to divide these two parameters. You know what I'm saying? And then you will essentially get the value. So once we do this, we should get our value of density, which again, always keep in mind the units because it's not mentioned here. The examiner wants to trick us. It is going to be 520 kilograms per meter cube. Describe an experiment to determine the speed of sound in air. So there are like a bunch of ways to go about with this. So I'll go with my favorite, which is the echo method. So in the echo method, you're going to have a person over here, which for example, he's holding like an instrument, like a trombone or something, okay? And then we're going to have another person standing right next to him. And there's going to be a wall ahead of them. So the first step is you're going to be measuring the distance between the person and the wall. And we're going to call this, for example, distance, okay? So let's say that this is person 1, this is person 2. So when person 1 like makes a noise, person 2 is going to start a stopwatch that he has. And essentially what's going to happen is this sound is going to travel to the wall. It's going to reflect back because of echo. And when he hears the second sound, that's when he stops the stopwatch. And when you have that, you have two variables right now. Ek though you have the distance, then you have the time that it took. Then we use a formula, which is going to be v is equal to 2 distance times time. Why 2 times distance? Because the sound wave travels one way distance and the other way back. So it is going to be d plus d, which is 2d. So essentially, this is how we're going to frame our answer. We're going to talk about how we require two people, a stopwatch, trundle wheel, and a wall. This is going to be a trundle wheel. It's for measuring long distances like beyond 1 meter. Then we're going to measure the distance using a trundle wheel. Person 1 makes a clapping sound. Person 2 starts stopwatch when he hears it and then stops when the echo is heard. Again, we're just describing what we did. And then we apply the formula v is equal to 2 times distance divided by time. Here is a full-size diagram of a lens and an image eye of an object. Now, this is probably the trickiest topic so far in physics. So let's just go over this real quick. The focal length of the lens is 3 centimeters. Mark 2 points with labels F to show the positions of the principal focuses of the lens. Now, to understand lenses, you firstly need to understand these terms like focal point. So focal point is essentially that point on the axis, the principal axis. This is the principal axis, by the way. It's the point on the axis where all the rays converge, where they meet. So the question is, luckily enough, the question tells us that it is at 3 centimeters. So all we got to do is just use our scale. For example, you have your ruler with you in the exam. Obviously, you're going to have that. Please don't forget to bring that. 3 centimeters from the center point of the lens. So this is going to be like, for example, it's going to be right over here. So this is going to be F. And similarly, equidistant, it's going to be another F over here. And maybe it's a bit to the left, actually. So this is how we figure out the principal focus. So the next part is on figure 6.1, draw two rays from the image to locate the object, draw the object and label it. Oh, the question is asking us to draw two rays, but for like future purposes, I'm going to draw three. So we're going to have the first ray that directly crosses the midline. So always remember this. The first ray is always going to be crossing the midline of this lens over here, right where it meets the principal axis. Okay, so this is going to be the center. Then we're going to have a second ray, which for example is moving. First of all, this ray moves to the midline of the lens and then it cuts the F point, the focal point. So we're going to see something like this over here. Then we're going to have a third one, for example, and this third one actually starts off from here. It cuts through the F again, like we mentioned, and it's going to touch the midline and then become straight. So we can kind of see a pattern over here. Obviously, I haven't drawn these Fs like in equal distances. That's why it looks weird. But essentially, we're going to reach a point where they all three intersect. Let's say that this is the point where they intersect. And this point of intersection is where the object is going to be viewed as the image. So we're going to go up and we can see that this object is inverted as well. And so now we have the next part, which is if the object is moved so that it is 6 centimeters to the left of the lens. Now to understand this, we know that the focal point is what? 3 centimeters. So now essentially the object is going to be where? 6 centimeters, which is essentially also 2 times the focal length. Now we have specific rules for the image formed if we have like different situations where the object is placed depending on its position relative to the focal point. So for now, all you gotta know is that if the object is at a position where it is at 2f, the image is going to be real, it is going to be inverted, and it is going to be the same size as the object. So here is going to be our answer. Okay, moving on, now we have this circuit over here with a bunch of resistors and a voltmeter. So ABCD are identical. The current in resistor A is 2.4 amps. State the value of the current in resistor B, explain your answer. So we know that the value of current passing through A is 2.4. And we know that these are all identical. So since A and D are identical, we can just say that the current over here is also 2.4. Why is that? Because again, the current is all coming from this one source over here and it starts splitting depending on the resistance, okay? So we can see that since A and D are similar in resistance within the parallel circuit, then we see over here that this is again going to have the same current supply. Now that we've dealt with D, since B and C are in a series circuit within this whole parallel combination, we know that the resistance of this part is going to be 2 times the resistance of A, for example, okay? And what that means is we know the formula of V is equal to I R, right? We know that I is equal to V divided by R. And over here, we can see an inverse proportionality, which essentially means that if the resistance were to increase, the current decreases. So over here, we'll see that since the resistance increases by 2, the current should also decrease by 2, okay? So we're going to say that the current in resistor B is 1.2, and the reason is because the resistors in series double up. Now that we have the current in resistor B, we can easily find the value of I next, because we know that the original I split into different branches. So it's going to be 2.4 plus 1.2 amps plus 2.4, which should amount to 6. So the answer over here is going to be 6.08. Don't forget the units. The reading on the voltmeter is 5. Calculate the resistance of resistor A. So resistor A is 2. So we know that in a parallel circuit, always remember, in parallel combinations, the current splits, but the voltage remains the same. What that essentially means is that each component within the parallel circuit is going to be receiving the same voltage, which is 5. So we know that V is equal to IR. We know that 5 volts is equal to I, which was 2.4 times R. And now we know that when we divide these, we're going to get 2.1 ohms. Next up, we have rubber balloon is inflated with helium, okay, and sealed so that no helium escapes. Here we have a balloon, blah, blah, blah. When the heaters are first switched on, the temperature of the air immediately below the ceiling increases and more quickly than the temperature in the rest of the room. Now, this is known as conventional current. We have the room over here, right? There's going to be a heater over here, for example. It's going to be giving off warm air. Now, since warm air has low density, why does it have low density? Because the particles are moving quickly, they're spaced far apart. So we're going to see that the warm air rises up more and the cooler air goes down to replace the warmer air. So we will see that below the ceiling over here, there's going to be more temperature rise. So essentially, we're going to mention something like warmer air is less dense, so it rises, and because of it rising, the temperature increases, and the colder air replaces the displaces the warmer air. So next up, we have as the rubber stretches and the volume increases, the pressure remains constant. Now, this is an interesting question and unique as well. So first of all, let's address the situation. So to understand this, we know that there's a balloon over here. It has helium particles around it. Now, if you're going to increase the temperature, what's going to happen? They're going to collide with the balloons with more force, the walls of the balloon. And because of that, you're going to see that the balloon starts expanding, okay, just like this. Now, because of the balloon expanding, what do we see? We see that the volume increases. Since the volume increases, what happens to the surface area? The surface area also increases. So we kind of see why pressure isn't affected over here. Why? Because pressure is equal to force divided by area. So if the force is increasing because more helium particles are colliding with the walls, and the area is increasing because the volume is increasing, then pressure won't really change, like they cancel each other out. Another way of thinking about this is, as the volume increases, the helium atoms or particles, they actually don't really collide with the walls as often because there is more space now. So the frequency of collisions decrease. That is also another way of thinking about it. This is how we're going to essentially word our answer. Higher temperature means that the particles collide with more force, and so the volume increases, leading to an increased surface area for collisions. So the effect of large surface area cancels the large force. Here we have question 5. We have a block ABCD made of glass that has a refractive index of 1.5. There's a curved side and then 3 straight sides. So AB is the curved side. There are right angles at C and D. The curved side AB is 1/4 of the circumference of a circle that has its center at. Okay, what is exactly happening here, man? So there are right angles at C and D. So we can see that there are right angles over here. And the curved side is 1/4 of the circumference of a circle. So we can see that this is a quarter of a circle. Like this is a circle, we can divide this into a quarter. Then we can see that the midpoint is point number P. So a ray of monochromatic light enters the block through the curved side and strikes side BC at P. Some light emerges. Let's go to the questions. What is meant by monochromatic? So monochromatic, you could say, is light of a single frequency. Explain why the ray of light does not change direction when it enters the block through side AB. So we can see that it does not change sides because if you guys remember about drawing angles in refraction, we have a line called the normal, and this monochromatic light is passing straight through that normal line without any like deviation in angle. So that is why the light is just going to pass straight through. If the monochromatic light was coming in this direction, for example, right over here, then we would see that this actually does deviate. It would pass towards the normal like this. But since it's passing in the direction of the normal, it's like parallel to it, then there's going to be no change. So in terms of angles, we should say something like angle of incidence is 0 because again, it's parallel to the normal, and the angle of refraction is 0 as well. So these are the two marks that you need for this question. Moving on, show that the critical angle C for glass of refractive index 1.5 is 42 degrees. So this one's not really that difficult. The formula that you need to know is the refractive index is equal to 1 over sine critical angle. And we know that if you want to make C the subject, what happens is it becomes 1 over n sine inverse right over here. So figure 5.1 shows that the angle between the ray of light and the line AP is theta, where the line AP is at right angles to side BC. What happens to the light that strikes P? So in this part of the question, which is given that there is a line AP that is at right angle to BC, and we can see that there is indeed a right angle over here that can be formed. And we can see that there is an angle between them. Now, if this angle is increased to 45, what's going to happen? There's going to be total internal reflection. Why? Because the angle over here, the angle of incidence is greater than the critical angle. So hopefully this is clear. I mean, there's not much concept to this. You just got to know that if the angle of incidence, the angle at which it is striking, is greater than the critical angle, then there's going to be reflection. Now, when theta is 45, the reflected light strikes CD. Describe what happens when this reflected light strikes CD.
So if you imagine the question, we see that there's going to be a light at 45 degrees, let's say for example, striking over here.
So we're going to see that there's going to be another ray that reflects in this direction. And this ray that is being reflected is going to be parallel to the original ray. You can see the similarities between these two rays. So again, this should be our answer, where reflected ray is parallel to the original ray. If you guys have any questions, do let me know. I'm going to be starting a series on ATP as well, since that is coming up. And yeah, I'll see you guys next video. Take care.